Swayam Prabha. Digital India. Educated India.
In the last class, we were looking at the governing equation for dynamics. And we had, in fact, derived a very general expression for a body where the coordinates are centered at its, say, CG location, for example. And that we said this is the body-centered coordinates. Okay? We looked at the inertial frame of reference. And we also found out that there are some additional terms that are required, especially when the body-centered coordinates, or in other words, which is attached to the body of, say, for example, vehicle. And if it now starts moving, the vehicle starts moving as well as it's rotating and so on, the body-centered coordinates also rotates along with it. And hence, certain changes are needed. Okay, some additional terms are required in order that we take into account this motion of the body, right? This is what we said, and we derived a very general three-dimensional expression, right, for this body-centered coordinates. You would have studied this in dynamics. Anyway, that's a refresher. What I'm going to do is that some of the things which you would have studied, anyway, we'll go back and just refresh it a bit so that you will know that I'm going to apply what you had studied before. I'm going to do that. For example, you would have done a course on control systems. I'm going to do that again here in today's lecture. Right. So ultimately, as is usually the case in engineering, you start with a grand, equation, and then slowly say that, this I will neglect, that I'll neglect, this I'll neglect, that I'll neglect, so that, it ultimately becomes, so to say, handleable. Okay, so that you don't lose the physics. At the same time, the equations are simple. This is a usual fact of life in engineering. So we will write that way, okay, for what is called as a bicycle model. So that's the bicycle model which we had just started. Okay, so what I told, please remember what I said in the last class, that I'm going to collapse the two wheels, okay, into one, both in the front and the rear. Hence, it looks like a bicycle, so it's called a bicycle model, nothing to do with actual bicycle, stability of bicycle and so on. It's just called a bicycle model because it has two wheels. Collapse the two wheels into one wheel. The result of collapsing this is to reduce the degrees of freedom. Okay? So I'm going to look at this with, or in other words, the equations which I'm going to write down with consists of V and R, where R is the yaw rate, right? So we already said that R is going to be the yaw rate, right? We are going to look at a system where U is a constant. In other words, it's a steady state. U is equal to a constant U. We are not going to vary U, and we're going to write down all the equations in terms of V and R. In other words, my differential equation, which I'm going to reduce that huge guy, 6 equations, into simple 2 equations. Okay? So I'm going to write down that equation into IZR dot. What is IZR dot? It's equal to tau. It is the yaw which is perpendicular to the plane of the board. Okay? So for that, I need to put down the forces. So that's the force F alpha R. Let me, okay, FR or F alpha R. Why alpha R? Because as I told you before, alpha R is the slip angle and F alpha R is the result of this alpha R. In the same fashion, we will put down a force that's acting in the front and we'll call this as f alpha f. These angles are very small, so I'll make a lot of, again, assumptions there. The whole idea most of the time is to bring down the equations to a linear range. The whole question in engineering is whether that assumption is valid, whether are you really operating in the linear range, and so on. Okay? Sometimes you won't be, and that's where your judgment matters. Let's finish these expressions, and then we will come back to, we'll take the questions. Okay. Now let's look at the front. So this is the alpha r, this is the f alpha r. Let's look at the front. The front, you have, I hope this is not a very confusing picture. Maybe I will use a chalk piece. So I have first, look at that. So that is what is the steering angle I have given. Okay? So that green one is the steering angle. Okay? I have no, this is not, I'm not steering the rear wheel. It's possible to do that. There are a lot of interesting things that happen when you can steer the rear wheel as well. For example, if you have huge vehicles, for example, vehicles which are used by space agencies, where they want to transport the rockets which are to be launched. So you would see that there are 32 axles, okay, or 64 axles, huge ones, where you can't obviously drive them with only one driven axle, or a steered axle, sorry. So it has to be more than one. The problem becomes very interesting. Well, let's not get into all that. We are only looking at now the front axle steered vehicle. So that's the alpha r, and the alpha r, okay, delta r, which is the delta f rather, or delta, okay, and that since I have to develop a force, note that force requirement is that I develop a slip angle which I call as alpha f, right? That's the slip angle. So with the result that I get the force which is f alpha f. Okay, so let's we'll keep that as alpha f and alpha r. If you want front y, and that will be easier. This is f front in the y direction, and f rear in the y direction. Either way, you can call this as alpha r, or doesn't matter, as long as you understand what we are talking about. Okay. No. This is the turning. Please note that. Please understand the coordinate system. We are going to take a turn. Okay. This is some sort of a plan view. Okay. You are looking at x and y. Okay. And that's x, y, and the z is into the ground. Right. That's the coordinate. So you're looking at a plan view of the vehicle. Right? So obviously, Fy is a centripetal force. So this is equal to the moment. Okay. So what is that? A into Fy front, or Fyf. It's easy to call that as Fyf, because many books, the problem why I'm writing like this is because if you follow a textbook, then he would have given different terminology. You have to understand that clearly. Fyf minus B into Fyr. Okay, y in the rear direction, right? So what's the second expression? It is, go back and look at what we had done, m v dot plus ru. So it's not m v dot because of the body-centered coordinates, m v dot plus ru, and that is equal to Fyf plus Fyr. Okay, so these are the two expressions we have. Now I'm going to use again the dynamics along with geometry in order to write down deltas and so on. Now let me define a new term. I hope you will not confused with that. Okay, which I would call as beta. Obviously, there is a V, there's a U, okay, and hence vehicle actually moves along this angle beta, okay, that is the angle beta. And beta is called as the vehicle slip angle. I'll call beta as the vehicle slip angle. Obviously, from this diagram, okay, so you have you have that angle beta, and so that is V. So tan beta is equal to V by U. Right? Okay. Now let us look at alpha r. Now I have a r. R is now, what is r? We said that it is the yaw rate. Okay? So if I have to write down the velocity at the rear, this is the velocity v and u are at the CG location. Okay? Hence, if I have to write down the velocity at the rear, what would be the velocity? There would be, look at this, there would be a velocity which is due to r, which is b into r, right? That will be, I'll just put that here and then transfer it there. So that will be in this direction, right? B into r. There will be a velocity which is v in this direction. That will be a v in this direction. Okay? So b into r is due to r, and v is the velocity. So when you transfer the velocity, it becomes v, okay, and br. Since it is in the opposite direction, okay, I can write that as, so in this direction I can write that as br minus v, okay, br minus v, and tan alpha r, because that is, that's in the opposite direction to our coordinate system, that becomes divided by u. Okay, that's very simple. Look at that. Clear?
Longitudinal velocity will be same for both the
Yeah, of course. Longitudinal velocity u is constant. We are not touching u, so that's the same, because the vehicle is moving in the same direction with a constant velocity u.
Here we are assuming that contact fraction.
So in other words, please note this. In other words, when I have to look at u, the variation of u, I am looking at longitudinal dynamics. The first equation in what we did in the last class, we had, what's that we have done? We have looked at the first equation in the last class. So we had looked at the longitudinal dynamics. Now I'm going to remove the longitudinal dynamics. Okay? So I'm saying now that I'm going to only look at the lateral dynamics. So that's what we are going to do now. Right? Okay.
Here fly steer and conicity.
Yeah, right. We will come to that. We have not looked at tire yet. I'm going to have a very simple tire model. Okay? Ply steer, conicity, all those things will come. Everything we'll have to then put the model. Just wait for some time. Let's finish this. Right? Just hold your questions. Let's go forward. Many of your questions will be answered as we go forward. I'm going to make a assumption that tan alpha r is approximately equal to alpha r. So alpha r is equal to v by u minus b into r by u. Right? Okay, I'm just going to. So what is v by u? We had already seen that v by u is beta, tan beta, which is again approximately equal to beta. So that's equal to beta. Let's let's assume that this vehicle is taking a turn and the turning radius is equal to R, capital R. So R is the, let's say that R is the turning radius. I'll finish this here and write it down there. So now, how do I write the second expression? R is like omega, u is the tangential velocity, so that is equal to radius of, that is the R, omega R, R into R is equal to u, so R by, right, R by u, so that's equal to minus B by R, right. So the first expression of interest to us, I will write down here, I will do all these things there. So alpha R is equal to beta minus B by R. That's my first expression. Let's now look at alpha F. Is there any questions, right? Similar way, I will look at alpha F.
So here is acting in the tangential direction of the here has to act in the direction of tangential. Here is acting in
Which one?
Here is acting in vertical direction. Left side direction. Actually, here is acting in tangential.
No, this is the, no. Please understand that. Let's just wait for some time. Let's finish this expression. Okay? We'll take the questions towards the end. If there's, just hold your questions. We will do that later. So just say that, see, this is an R. Okay? R is positive. Positive is right hand side, so inside. So you will see that this is the tangential velocity here. Due to R is actually in this direction. So B into R is in that direction. That's all we have said. Okay? Closely watch. That is why I'd put one BR like that and V like this. Clear? Now I have to write alpha F. Okay? So what is alpha F? Look at that. This whole thing is delta. Okay? And that is alpha F. So alpha F is equal to delta, I'm just giving a small gap there. So here, that is BR, this is now AR, right? A into R. A into R, that's in the same direction as that of V. So you will get delta minus, that is the AR plus V divided by U. Now, note that alpha F is in a direction which is in the negative direction of Z. So I'm going to put a minus here. Okay? So I have to be careful because note that a negative direction alpha F produces a positive Fy. Okay? So that's why I put a negative so that I'm clear. So I don't have confusion. So many books you would see that it is alpha F, and when I develop FYF or Fy, it is just multiplied by C alpha multiplied by alpha. Okay, there's a small confusion. There's nothing wrong with this, but you have to be very careful on the way you are writing it. Okay, so I'm going to write that. You will see that I'll put two minuses, so that I'll take care of that. Clearly, the signs are clear. Okay. Now simplify that. Let's say that I'm going to simplify that expression. Minus delta minus AR by U. Okay. So that is equal to minus A by R minus beta. Right? So that delta now can be written in terms of alpha. Bring the delta the other side. And then rewrite that expression, okay, and substitute this expression for beta, substitute that into this expression, and you rewrite that expression. So in other words, I can say that when I take it delta the other side. Yeah, any questions?
So what is R like in this?
Note the difference between capital R and small r.
I know that, but what like it signifies in this model like
Small r.
capital R?
Capital R is the radius of this turning, the turning radius. Actually, let me give a bigger picture. You're taking a turn, okay? So your vehicle is here, and that radius of your turn is equal to capital R, right? So rearranging the terms, this becomes L by R, because A plus B is equal to L minus alpha F plus alpha R. Clear? Okay. Now, we will come to the tire model. There are a number of, as I told you, there are a number of tire models available. We will go only for a simple model because I want to capture the physics of maneuvering. So that I will write down Fy to be minus C alpha into alpha. So why am I writing this as minus? Because I know that a negative alpha produces a positive Fy. Okay, a negative alpha produces a positive Fy. So in other words, when I put alpha to be negative, actually it becomes Fy becomes positive. So that's why you put a minus. There are books which treat this to be negative, which is not correct. Okay, C alpha stiffness is not correct. So this is a simple model. What is this model? This is a linear model. So in other words, we saw already that, okay, there is a region, that's the, suppose I plot alpha versus Fy. We saw that the curve looks something like this, and I'm going to take a linear model where that is the slope is what I call a C alpha. Okay, so C alpha into alpha gives me Fy. So this is a simple linear model. From here, when I put Fy front, I put C alpha F into alpha F, and Fy R, I put minus C alpha R into alpha R. Clear? Okay. Now, so that Fy now, the total Fy, note that this is a general expression, I'm just going to remove it so that you don't get confused. So now Fy is equal to Fyf plus Fyr, and that is equal to minus C alpha F into alpha F minus C alpha R into alpha R. Right?
Sir, is C alpha your stiffness?
Yeah, of course. Right? I'll give you a small job. Write down alpha F and alpha R. We had already derived it, if I think it's there in that expression. So just put that. So minus is that, so just substitute it. Minus of that. So I'm going to write down completely the final expression. You can look at the final expression, that is equal to minus A by U C alpha F plus B by U C alpha r into r minus C alpha f plus C alpha r into beta plus C alpha f into delta. So that is going to be my Fy. The second term, the second is minus A into C alpha f into alpha f, okay, plus B into C alpha r into alpha r. Substitute that so that mz is equal to minus A squared by u C alpha f minus B squared by u C alpha r Okay, so substituting that, you get these two expressions. Now, what is the next step? What's the next step? I have Fy and Mz. Go and substitute it back into my expression or my governing equation. Okay, substitute that into governing equation. So I get, these are the two equations. Now what I have essentially done is to write down the right hand side. Okay, so write down the right hand side. I have written down the right hand side, and so I have now, okay, substitute that back and write down the complete equation. Okay, the left hand side and the right hand side. Right. I'm going to, now what are the two variables or two degrees of freedom here? R, not U, R and V. R and V. A by R. Which one?
Minus A by M.
B by R, right? Okay. What? No, I have put R outside. Oh, sorry. I have put R outside, so that's U here. U is fine. R is outside here. Okay? R is outside, and that's fine. Now I'm going to rewrite this expression, okay, substitute that and rewrite this expression in a very familiar form. Okay. So those two equations you know. So those are the two expressions I'm going. So it's very simple. Only thing is you have to be careful in that algebra. So the first expression now becomes, I don't want to rewrite it. I z r dot is equal to mz. That's the one, and that's the second expression. Now I'm going to write this down. I leave a couple of steps to you to do it. It's nothing. In a form which is familiar to you. I'm going to write this as V. What are the things that are available there, or over my expressions? So V dot. Okay, that's the second expression I have, and R dot. Okay, those are the two things. I'm going to write down that as A. Readjust those terms. V R, right, plus B into delta, right? Essentially, what is that I have done? I have just put that, rearranged the terms. Clear? Any questions? Nothing. No big calculations. If I now put that form, when I rearrange it, I'm going to I'm going to write that final form, V dot R dot is equal to minus C alpha F plus C alpha R divided by mu. I think it's good to have that expression this we had. I Z R dot is equal to AC alpha F minus BC alpha R, this one right? Yeah. And M into V dot plus RU is equal to Fy. Okay? So R dot and V dot, that's what we're writing there. Minus AC alpha F plus BC alpha R by mu minus u, that's the second term, and minus AC alpha F minus BC alpha R divided by IU minus A squared C alpha F plus B squared C alpha R divided by IU. Okay, that would be my A, and V R plus C alpha F by M AC alpha F by I delta. Okay. Any questions on this? I've skipped 2 or 3 simple lines which I think you can fill up. Now, this is a familiar form to you. Right? This is a very familiar form to you. What is this form? What is this called as? State space form. Okay? So this is nothing but a state space form. What are the state variables here? V and R. Okay? The whole idea of writing this in a state space form is to look at the stability of the system. That's the first idea. Later that we will use this in order to look at the response of the vehicle to dynamic inputs, which is the steering input, right? So the first job here is to look at stability of the system. Now I will take questions. Any questions? Okay. The only thing you have to be careful is C alpha F, C alpha R minus plus, whatever you want to use it, it is fine as long as ultimately Fy is in the positive direction, right? So that you have to be, that's the only thing you have to be careful. Whatever you do, ultimately you will get that expression only. So minus to minus, plus and all that, you would get only that expression. Okay. So now we are going to look at the stability of a system. Okay. What do we? Yeah.
U is also input, right?
U is, yes, U is a particular velocity. Okay, it doesn't change, but it's an input. Right? It doesn't change. We're not going to calculate it. Right? Okay. Please understand this is a lateral dynamics. So what do we mean by stability of the system? How do we determine the stability of the system? The immediate thing that comes to your mind when we talk about stability of the system is an eigenvalue problem, right? So you had studied that in your control system course, and that there is no input, the right hand side is equal to 0. Okay? So, and then the left hand side, which is the governing equation, right hand side, which is the F, okay, is put to 0. You go back and solve for the eigenvalues and so on and so forth. This is what you've been doing. Okay? Here also you have to understand this carefully. Now, we are going to do exactly the same thing. We are going to put the inputs to the system to be equal to 0. In other words, In other words, I'm going to put delta to be equal to 0. This is the input to the system. This is equal to 0. Now, there's a confusion. If I put delta is equal to 0, which means that actually I go straight. Now, what is that I'm doing? When I go straight and I'm putting delta is equal to 0, and we are talking about stability in the lateral dynamics, okay, then what does it mean? Right? That's the question. So, for that you have to understand what we mean by stability. This is a usual thing because we are going to apply the concept of stability. So, we have to understand what is stability. Even if you are going straight, okay, we say that the system is stable in simple terms when there is a perturbation to the system. The perturbation can be due to some suddenly wind that is blowing, or due to a pothole you take a small turn and so on. You know, a perturbation to the system you give, the system returns back to its equilibrium position. What is an equilibrium position? The system continues to be in that position unless it is forced to move out due to an input. So, a small perturbation which you give, it gets back to its equilibrium position. Okay? So, that is why you put a very high school example of putting a ball in a well, and when you distribute it, when you disturb it, it comes back to this position because you are actually perturbing the ball about an equilibrium position, okay, and then it gets back to the. So that is the philosophy here, okay. In other words, you cannot make a statement which I have seen many people making. I am not going when I don't take a turn in a vehicle, okay. Why am I worried about stability of the system? No, it's not true. Even if you go straight, a small perturbation, okay, is enough to cause an unstable, for the system to become unstable, right? So keep this in mind because this is going to be very useful for us to interpret the results later, right? So we will get into what is meant by stability, how do you calculate stability and so on. Maybe you have done this before, but we will do that again quickly, okay? Now, generally a system is expressed in terms of a differential equation, okay, which we will say that a dt power n, or we will put that as dt power n plus a n minus 1 d n minus 1 x dt n minus 1. Okay, this is the nth order system, so the last term should be available plus an into x is equal to 0. Note that an cannot be 0 if you are looking at an nth order system. Okay, this is a0 into. Many times you write it the other way. You can write this to be 0, 1, and also as n. Okay, either way you do that. Textbooks follow different procedures. You can also write down, okay, this is a differential equation form. The most immediate application, if you look at this, is in dynamics, is your vibration equation. You can write it as mx double dot plus cx dot plus kx. Okay, you can also write this down in the state space form which we had written down, okay, which I can write down as x dot 1, okay, in terms of what are called the state variables. X dot 1 is equal to a11 x1 plus a12 x2 plus so on plus a1n xn, and then x dot 2 is equal to a21 x1 plus a22 x2 plus, and then so that x dot 1 x dot 2 x dot n is equal to a x, okay. is another way of writing it down. There are two ways in which you can write down. It doesn't matter in what way you write down. Okay. If I want to look at the solution of this equation, the solution of the equation can be written as x of t is equal to x e power st. Okay. The solution of the equation can be written as x of t is equal to x e power st. This form of equation is valid only if we have certain characteristics for S. I can't put any S. Of course, S has, it can be real or imaginary and so on and so forth. We will come to that in a minute. So this this S, okay, has a characteristics which you would have studied in your earlier courses, and we will see what this characteristics of S has to be, or what should this S be, okay, in order that this becomes a solution to the system, right? Since x is equal to this thing, x dot t is equal to S x e power st, and x double dot t is equal to S squared x e power st, and so on. Substituting that into the governing equation, we will do that for this case in a minute, right. So substituting that in that expression, what is that you get? A naught s power n plus a1 s power n minus 1 plus so on plus an e power st x e power st is equal to 0. Right? Okay. The next step is obvious. We have done this. What is that? For the non-trivial solution to exist, okay, this has to be equal to 0. Okay. What is the trivial solution? X is equal to 0, because once this is not equal to 0, then x has to be equal to 0, and that's a trivial solution. So the trivial solution or non-trivial solution to exist plus a1 s power n minus 1 plus an is equal to 0 for non-trivial solution. Okay. So there are, S is nothing but the roots of this equation. There are n roots, and so the solution of the equation can be expressed as the sum of these roots and so on, right? Okay. Now that's known. Now let us now look at the state space form. Please understand that this is one way. There is no unique way of writing. This is one way of writing the state space. It's not necessary that you will have, or you need to follow only a set called x dot 1, x dot 2, x dot and so on for state space. You can have another form as the state variables, okay, and express this equation in another form. Doesn't matter, you will ultimately see that the stability of the system obviously will not be affected by the way you write down the state space equation. Clear? Okay. So let us now look at how to write this. This is clear. It's exactly now extended here. So how do I write this? Instead of x, I'll write that as x e est. Okay. So that x dot now becomes S X E S T. Substitute that into this expression. Okay, x dot is equal to Ax S X E S T, okay, is equal to A X E S T put an I here, so that, which is the identity matrix, right? And so I will write this down as Si minus A into X E S T is equal to 0. Okay, this is just a revision. I know you guys know this. Once we finish it, we will go and apply it to this expression. That's what we are going to do. So for a non-trivial solution for this expression to exist, what's it? What is determinant of this? That's the characteristic. That's what is called as the characteristic equation. And so the same condition for non-trivial solution to exist. So the determinant of S of I minus A should be equal to 0. Or else, okay, that's simple. Or else, if it happens to be non-singular, then obviously you will end up with only the trivial solution. Hence, this has to be equal to 0. And that throws up values of S. Yes.
Assuming same frequency for all the variables. Same is.
No, S1, S2. No, that's what we are going to get now. S1 and S2. We are looking still at stability. Okay. We will come back to other quantities a bit later. Okay. We have not solved for S. We have not found out the eigenvalues yet. We are still looking at the equation for stability. What is the condition for stability? Right? I have not solved it yet for S1, S2 and so on. Right? For this. That's what I am going to do now. First, let me look at the stability of this equation.
Yes.
Yes, that's what I'm saying. Yes. Okay. I have not yet solved it. I'm just writing down. I said that there is S1 and S2. That's all. What are they? I have not yet determined them.
According to this, say my x1 is capital X1 into e power st, and
Yeah.
my x2 is capital X2 into again e power st. Like
Yeah. So we will S1 and S2 there will be two roots. Just wait for a minute. Let's finish this. We will look at that. That's what we did here. I wrote this. If it's a second order system, it will be S squared plus. That will be that's what I said, that there are n roots. Just wait for some time. Okay. Let's first finish it and then we will go to the stability. So now that is the determinant of that system should be equal to 0. Okay. Now what I'm going to do now is to express. I know what is A. That is A. That is A. Right? What I'm going to do is to substitute that A here and expand it and write down some quantity of S squared plus some quantity as S plus some quantity is equal to 0. What are those things? We will do that in the next class. Just quickly, so that you don't have a confusion as to what I'm doing. Right? So I'm going to write this down like this. Right? Then look at stability of the system. That's what first I'm doing. So look at stability of the system. The stability of the system for which an expression governing the characteristic equation is like this is given by a very simple criteria. Raoult's criteria, which states that what is here should be positive. If I call this as A0, this as A1, and this is A2, the necessary and sufficient condition is that A0, A1, and A2 should be positive. Okay? So that's the first thing I'm going to do. We're going to do problems later, okay, to look at the transient analysis and so on. Then we will see, we will rework this out and see how I'm going to write down expression of e power at, a matrix called e power at and so on. We will do that later, right? Okay. So my first step is to find out A0, A1, and A2 and see under what condition A0, A1, and A2 are going to be positive. So the question which we are going to answer in the next class is it possible for a system to be unstable, for a vehicle to be unstable? If so, under what condition the vehicle is going to be unstable? Okay? We'll finish this class by saying that note what I mean by unstable. If you're going straight, okay, it is possible that if the system is unstable or vehicle is unstable, a disturbance that comes out or comes about in your system may not die down and may not bring you back to your equilibrium position, right? So that is the unstable case, right? We will now, our job is to substitute A here, write down that expression. We'll do that in the next class.